thank you for the invitation to speak about this, for me, a fascinating topic. So the one big question is where all of the elements in the universe have come from. And for most of them, a lot of them anyway, we have a pretty good understanding that the lightest elements were made in the Big Bang, but because masses 5 and 8 have no stable isotopes, it's impossible to basically push beyond that during the Big Bang. Some other lighter elements can be made by fissioning on heavier elements. And the heavier elements up to rubidium are believed to be made primarily in stars and in stellar explosions, such as supernovae. And then beyond rubidium, from strontium to bismuth, half of the heavy isotopes in nature are made by a kind of a neutron capture process, which is relatively slow. We'll discuss the difference between slow and rapid. And this S process is believed to occur in relatively low mass stars during the billions of years that they exist as red giants. And these elements are slowly expelled into space during those years as red giants through stellar winds, and more of the material may be ejected in nova explosions. And the other half of the heaviest elements are more mysterious, where those isotopes came from. They're formed by a rapid capturing of neutrons. So it's called the R process. And there has been a lot of speculation about that, and that's the subject of this talk. One of the most spectacular events so far of this century, scientifically, was the observation of GW 170817, the gravitational wave observation of the first observed merger of two neutron stars. We've called this event a multi-messenger event, so that terminology has become very popular. It was observed in many different wave bands and many different sources from different kinds of energy. So it was first observed as gravitational waves using the LIGO, Hanford, and Livingston observatories. The VIRGO observatory was also involved in this and contributed some substantial information by not observing the event. It was observed in gamma rays by the Fermi and integral observatories, with a more or less typical kind of gamma ray burst known as a short gamma ray burst, although it was the weakest gamma ray burst, the least luminous gamma ray burst ever observed. And there are good reasons for that. But it was detected, that gamma ray burst was detected 2 seconds approximately after the detection of gravitational waves. And then following that, for the next several days, optical, ultraviolet, and infrared observatories, including the Hubble Space Telescope and more than 100 other observatories worldwide, observed an afterglow from this gamma ray burst that we call a kilonova. Later, X-rays observed from maximum Chandra Swift were observed, and even later millimeter and radio waves from many observatories were also detected. So it's believed that about 3,500 astronomers observed this event. Of the observational astronomers. There's fewer than 10,000 of them worldwide. So that shows you the remarkable characteristic of and the importance that this event was considered, that so many people were involved. So the term multi-messenger astronomy became quite popular in describing this event, but I would like to point out this was not the first multi-messenger observation or even event. I think the first multi-messenger observation, which combines both electromagnetic radiation and radiation of other sorts, I think it should be attributed to Ray Davis, who eventually won a Nobel Prize for his late 1960s discovery of solar neutrinos from a gold mine, repurposed gold mine in South Dakota in the US. Ray was a kind of chemist that we like to call a nuclear chemist. There aren't very many of them worldwide, but he's one of them. And his observation was a remarkable combination of chemistry and physics, in which he was able to isolate just a few atoms of a Nobel gas that was created from interactions with neutrinos in a huge tank, 100,000 gallons of perchloroethylene. And these few atoms would accumulate per week, and after a few months, he could then, in a fascinating process, be able to extract those radioactive atoms and observe them decay, and essentially be able to count the neutrino interactions as a result. So the first multi-messenger event, however, could be considered supernova 1987A, which is the closest supernova observed in several hundred years from the Earth in the Large Magellanic Cloud. So 51 kiloparsecs distance. And here again, neutrino observations were detected nearly simultaneously with optical information, although the neutrinos were detected a few hours before the first optical emission. And this can be accounted for by the fact that the shock wave that was produced by the event that created the neutrinos took several hours to propagate through the outer layers of the star until it emerged from the surface of the star and we could see the first optical emission. It's believed that neutrinos were observed from at least 3 neutrino detectors, including IMB, the Kamioka detector in Japan, and the Busan neutrino observatories. So this event occurred on February 23rd, 1987. And a remarkable piece of history is that the name 1987A means that it was the first supernova observed in that year. And that's 54 days after the beginning of the year. We barely have to wait 54 minutes after the beginning of the year now to observe the first supernova of a year. So the importance of supernovae, both for cosmology and for stellar evolution, was partially rekindled by the occurrence of supernova 1987A, and now we have dedicated neutrino optical observatories to the detection of supernovae in particular. So I just, this wasn't that long ago, and to think you wait 2 months to find a supernova, it just seems ridiculous from the present day perspective. This event was also very interesting in that it's one of the few events for which we know had observations of the star that became the supernova prior to the event. So a few days prior to the event, we have historical photographs, images from which you can actually see the giant star that is about to explode. So a total of about 20 neutrinos were observed during a period of 10 seconds. And from the energies of these neutrinos and times the number of neutrinos observed, and taking into account the masses of the detectors and their energy characteristics, one could infer that the total emitted energy and the total emitted energy from this event was roughly 3 × 10⁵ ergs, or 300 betas, another semi-equivalent unit. Which is the predicted gravitational binding energy of about a 1.4 solar mass, 12-kilometer radius neutron star. So this event by itself, with the neutrino detection, more or less proved what we already believed, that gravitational collapse supernovae, in this case, resulted in the formation of a neutron star, and that the optical energy that's observed is a tiny fraction, less than 1/100% of the total energy that's emitted, and 100 times as much energy, but still only 1% of the energy appears as the kinetic energy in the ejected material. But by far the vast majority of the energy appears as neutrino. In fact, in the first fraction of a second following the core collapse, the neutrino luminosity measured in Earth per second is basically equivalent to the total optical energy of all the stars observable in the universe for that short period of time. So the duration of the neutrinos was about 10 seconds, even though they were basically should have been produced over a much smaller time scale. But the fact is that they were impeded from emerging freely from the dense material because of the nuclear interactions with electrons and nucleons. So effectively, they became trapped in a star, much like the photons are trapped in the center of an ordinary star. Although photons are trapped for hundreds of millions of years in the sun, the neutrinos are trapped only for a few seconds in the dense protoneutron star core. But on the back of an envelope, one can show from the known characteristics of the interactions between neutrinos and nucleons and electrons that this time scale is completely consistent with the mass of a typical neutron star and with the typical radius of a neutron star. So that's something that was already anticipated. But the subject of the R process will have more to do, as we will see, with neutron stars rather than supernovae, we think. And neutron stars were an idea first conceived nearly simultaneously with the discovery of the neutron around 1932. Became a reality 32 years later when Jocelyn Bell at Cambridge helped build an array and discovered periodic emissions from a source in the sky, and eventually this is realized to be a rapidly rotating neutron star. The neutron stars have average densities a few times larger than we find in the center of an atomic nucleus, and with masses of about 1.4 solar masses, diameters of around 25 kilometers, which implies densities that are about 10 to the 15th times that of water. They're rapidly rotating and highly magnetized. The most rapidly rotating neutron star observed so far has a spin frequency of 700 hertz, which means that the velocity at the equator is something like 1/10 the speed of light or even greater. Magnetic fields, especially in magnetars, so-called magnetars, are enormous, ranging up to 10 to the 15th Gauss. And it's believed that electron-positron pairs created in the intense magnetic field, the magnetic poles generate beams of energy that emerge. And if the magnetic poles are not aligned with the rotational poles, then we have a beacon. And if the beam, believed to be a few tens of degrees in width, manages to pass by the Earth, we will observe the pulses. And these pulses were initially observed in radio by Jocelyn Bell, but we now know that the beams are also visible in many cases in optical and even gamma rays. So the outside of a neutron star, underneath a very thin atmosphere, from which X-rays can be observed, consists of a crust of very neutron-rich nuclei, and also neutrons that have been so-called are said to drip out of nuclei because the neutron chemical potential becomes positive. So we have nuclei in equilibrium with a fluid of neutrons and enough electrons to balance the charges of the protons in the nucleus. in the nuclei. Deeper, beyond the nuclear saturation density, at a few times 10 to the 14th grams per cubic centimeter, the material consists of a neutron-proton fluid, where the neutron-to-proton ratio is roughly 20. And interior to that, at higher densities, there may be a phase transition or a crossover transition to quark matter. I mean, most physicists believe that quarks will appear eventually when you squeeze nucleons to high enough density. We don't know where that occurs. The neutron stars is the only place in the universe where, outside of heavy ion colliders, where the production of quarks is common and may be common. So somewhere between 3,000 and 4,000 neutron stars are now observed, almost all of them in the form of pulsars. A few others as isolated neutron stars observed from thermal emission and gamma rays, others observed in binaries with other neutron stars that are pulsars, and a few as magnetars, as you can see. And they are all believed to have formed in the aftermath of supernovae. And as the Crab Nebula, the pulsar observed in the Crab Nebula shows that there is an intimate connection between supernovae and neutron stars. So GW 170817 was extremely important from a nucleosynthesis perspective. And just to summarize what was actually observed and what we might have learned from it, we can begin with the gravitational wave signal. Theoretically, you can easily calculate what that signal should look like from a pair of inspiraling compact objects. And one of the first easiest things to infer from the observation are the masses, or at least a combination of the masses, giving you roughly the total mass of the two neutron stars that were observed. So binaries consisting of neutron stars are not rare in the galaxy. We already know of 16 of them coming from pulsar observations in binaries. And although you can't definitively prove that the objects that were observed merging in GW 170817 were neutron stars, the signal is consistent with the interpretation that they were not black holes, but had finite sizes in which there were tidal effects. And from the estimates of the tidal deformabilities of these objects, one can estimate that their radii were in the range of 10 to 13 kilometers. So that's, again, typical neutron star sizes. The gravitational wave signal, besides telling us what the masses of the neutron stars were, also can lead to a distance measurement. And in this case, the distance was estimated to be 40 with about a 25%, 40 megaparsecs with about 25% uncertainty. As I said before, there was a weak short gamma ray burst following the gravitational wave signal and occurring from roughly the same location in the sky. And most astronomers believe that the short gamma ray burst can accompany a merger if the merged remnant eventually collapses into a black hole. So it's initially supported by differential rotation against this collapse, but the differential rotation should isotropize within a few tenths of a second, and then that angular momentum support is lost, and you collapse into believed you would then collapse into a black hole. And that sets up the conditions necessary to produce the beam that create the short gamma ray burst. Following this, there was electromagnetic radiation observed that lasted weeks and was consistent with roughly a 20th to a 10th of a solar mass of material that was ejected with velocities up to about a third the speed of light. And this also is helped by having the remnant collapse into a black hole. The inferred what you can also infer from this optical radiation is an estimate of the opacity of the ejected material. And it appears to be much higher than that of iron. And the opacities of the lanthanide elements are the highest known in nature. Yes. That's right. So this gamma ray burst was one of the weakest ever, the weakest ever observed, and it's believed because of observed off axis, which is probably not a unusual event. It's just that the gamma ray detectors, people have focused on the stronger bursts that have been observed, and the weaker bursts have not been followed up significantly. So we've probably missed most of these short gamma ray bursts that are observed off axis because they're just so weak and they're not worth, they didn't seem to be worth following up. People are going back now and looking more closely to get a more complete catalog of those. So if in fact the high opacity is due to the fact that some lanthanides elements were synthesized in this event, that could well solve the mystery then of where those particular elements originate in nature. And as we'll see, many of those elements are these process elements. So this is the gravitational wave event observed in the 3 observatories. So there's no indication in VIRGO of any event, but in LIGO and Hanford, you clearly see the signal. The vertical axis is the frequency, and the horizontal axis is in time. And as opposed to a typical black hole binary merger, in which you observe only a few tenths of a second prior to the merger, in this case, many hundreds of seconds of signal is extractable, and it finally culminates into, this isn't the merger itself. The signal is lost at around 200 to 300 hertz because of the sensitivity characteristics of the detector. The merger itself is probably close to 500 to 1,000 when the frequency becomes 500 to 1,000. So we missed actually a few of the orbits at the very end. And then the short gamma ray burst appeared shortly thereafterwards. If we line up the gamma ray observation, you see the gamma ray burst occurring. Then a few seconds after the projected merger would have occurred. The time delay is only a few seconds. And so this basically confirms that gravitational waves and light waves travel at essentially the same velocity. The probability of a chance event that this gamma ray burst was not connected with this event is believed to be extremely small. So there's certainly a connection between them. So this event basically confirms the hypothesis that was prevalent at the time, that short gamma ray bursts are connected with mergers, long gamma ray bursts are connected with a class of supernovae that may possibly very massive supernovae. So short gamma ray bursts have characteristic burst time scales of less than a couple of seconds, and long gamma ray bursts are longer. So in terms of determining where in the sky this event occurred, the detection with Hanford and Livingston detectors basically produced an error band, 2 error bands that are shown here and here, and the non-observation in the VIRGO detector, basically because of the dead spot of the VIRGO detector at any given time, actually helps triangulation quite a bit. And so this is the most likely region in the sky where the gravitational wave occurred. The gamma ray burst was observed by 2 detectors, integral and Fermi, and they don't have great localization, but the localization in the sky from integral and Fermi are certainly consistent with this gravitational wave detector. There was a 3rd gamma ray satellite that could have seen the gamma ray burst, but didn't, but because it was blocked by either the sun or the earth, I can't remember. So this region of the sky is invisible to it. So the fact that they didn't see it is also consistent in this case. So what one can do is to take this error region, here we're showing 68 and 90, 50%, 90% confidence intervals, and go to catalogs of the local universe, and basically, as a function of the masses, if you indicate by the size of the red dot here, you plot out those nearby galaxies. So these are the likely locations, the likely galaxies in which this merger occurred. And we can change this mapping in two-dimensional space, as a one dimension in space and one dimension in terms of distance. And so we can replot these galaxies now in this distance spatial representation. And the localization, the interpretation, the gravitational waves, as I said, gave us a distance of about 40 megaparsecs. So that's shown by this contour here. And if we then replot these galaxies, then we see that there are a few the galaxies that are most likely now are constrained by both distance and by time. And so as soon as optical observations were able to be initiated, a few hours, about 12 hours after the gravitational wave event, all of these galaxies were observed intensively. And this one particular galaxy, I think this one here, is shown here, had a glow outside of the central region indicated here, and its glow eventually disappeared, and that's characteristic of what we call kilonova, which are known have already been known to exist in conjunction with short gamma ray bursts. So we have identified in that way the galaxy in which this event occurred. So it's had long been predicted that mergers involving neutron stars could eject substantial amounts of material at very high velocities. And the nuclear physics basically is very straightforward to show that this decompression of neutron star material would lead to a rapid neutron capture, synthesizing extremely heavy elements. And those heavy elements would then have to decay back to normal nuclei, very heavy nuclei, and these decays, the beta decays and fissions, would result in the production of gamma rays, which would then have to be thermalized in the optically thick material that was ejected. And so eventually that energy should appear as optical and infrared energy, producing the kilonova. And they had long been believed to be the most likely source of the short gamma ray bursts. So this might have solved one of the long outstanding problems in nuclear physics, which is the origin of the production of this half of these heavy elements. And one can actually see the contributions of many, many different Nobel laureates to this development of this history of the ER process, which we will proceed to cover. The story about the existence of the ER process and debate about where the ER process elements came from stems back to the first tabular the first tables of abundances of the elements. And one of the first persons to study the composition of the Earth's crust and try to make an estimate of the abundances as a function of atomic number was a geochemist, American geochemist Frank Wigglesworth Clark in 1889. And so this is his abundance chart. It shows a characteristic feature that is a function of atomic number. The abundances rapidly decrease. And that's more or less expected on the grounds that if you form heavy elements by fusion, that it's just going to take longer times and to form heavy elements rather than lighter ones. There were no clear patterns that emerged from this study, but it's interesting historically. The Clark is a geochemical abundance unit, now, for example. A better compilation was made in 1938 by Goldschmidt, who looked at meteorite abundances as being more characteristic of the actual raw material that the solar system was made from, rather than looking at terrestrial compositions. And this is a paper. This is a figure using Goldschmidt's abundances, showing Goldschmidt's abundances as a function of A, taken from a famous alpha beta gamma paper published in 1948. This paper is interesting in a number of ways. This was actually the work of Alpher and Gamow and collaborators. And Gamow, who was the famous jokester, convinced Hans Bethe, who had nothing to do with his research, to contribute his name so that it could be the alpha beta gamma paper. Today this would be considered unethical. You just put your name on a paper. But full disclosure, Bethe, tried to get out of the, held off for a long time, but Gamma finally convinced him that no, you need to do this. But this had other consequences that we'll talk about as well. But the Goldschmidt meteoritic abundances showed an interesting feature that hadn't showed up before, namely that there were 3 peaks of heavy elements, and each peak is double. Each of those peaks are double in nature. And this is what basically inspired the fact that there were 2 peaks, or not that there were 2 peaks, but that the fact that there were these 3 sets of peaks inspired Maria Geppert-Mayer into the development of the shell model. And she developed that model, and in 1948, independently, Jensen also came up with a very similar model. And these peaks are connected with the so-called neutron magic numbers at 50, 82, and 126. The word, so Maria Geppert-Mayer didn't use the word magic number. It was actually Wigner who coined the term magic number as sarcasm, for being somewhat critical of this simplistic shell model idea. And it's rather ironic that Mayer and Jensen shared the Nobel Prize in 1948 with Wigner, who got it for some completely different discovery. Wigner got half the prize in that year, and Mayer and Jensen shared the other prize of the year. And so we've already seen one case of misogyny in the refusal of the Nobel Committee to award the Nobel Prize to Jocelyn Bell. There's another interesting case that occurs here. Mayer submitted her paper before Jensen, but they both to the same journal. But when Mayer realized that Jensen had also submitted a paper, she contacted the editor and said, why don't we hold off on publishing my paper so that both of them can be published in the same issue? It turns out that the publication of Jensen's paper occurred before that of Mayer. Fortunately, she did share the Nobel Prize, so I guess the long-term consequences weren't so substantial in this case. Anyway, the idea is that when NRZ equals one of these so-called magic numbers, then a nucleon shell, like atomic shells, are closed, and those nuclei become particularly stable and therefore abundant. I'll get back to this chart again in a minute. So then the question turned to where in the universe might these heavy elements have originated? Boyle basically established the principle that these heavy elements require some sort of explosive condition, most likely found in core collapse of massive stars. Alpha, beta, and gamma paper published in 1948, and also I think Gamma also arranged this. It would be published on April 1st, April Fool's Day. Basically put forth the idea that the neutron captures occurred to produce these heavy elements during the Big Bang. That model fails, obviously, because there are no stable isotopes at masses 5 or 8, so you can't just keep capturing neutrons and work your way up to the heavy elements. However, the more substantial contribution of that paper was in establishing that the Big Bang should result in the cosmic microwave background. And in fact, it has a prediction of the temperature of, I think it's 5 degrees, very close to the eventually discovered result. And Ralph Herman was an equal contributor to with Alpher on this idea, and Gamow as an advisor basically was also connected with the paper, but it was Alpher and Herman that did the real work on this. Gamow tried to convince Herman to change his name to Delter to be on this paper, and Herman was upset that Beta was being added to the paper because he thought it would diminish the contributions of Alpher and himself, so he refused to do this. So Alpher and Herman published later papers detailing the ideas that led to the prediction of the cosmic microwave background. So the bad part of adding Beta to the paper was the fact that Herman does not receive the recognition that he's due for this amazing prediction. And in fact, even in the Nobel Prize that it was awarded for the discovery of the cosmic microwave background, there's no mention of Alpher or Herman, even though they had predicted it theoretically. Anyway, the abundance of the elements continues with Seuss and Urey, famous abundance table from 1956. They were the first to take meteoritic abundances together with solar and terrestrial data to make a more complete abundance table. And this chart showing the Seuss and Urey abundances comes from the famous piece where the Baker paper in 1957. And basically see that for the heavy elements, these three double peaks. And after the appearance of these abundances, Coriell, in an unpublished science report, basically was the first to suggest that the fact that the peaks were double indicates that there's two processes involved in the neutron captures. One is slow and one is rapid, and with the slow peak appearing at larger mass than the rapid peak. And that's easily explainable, as I'll get to in a minute. He also suggested that the smoothness of the abundances was much greater if you just plotted odd elements or even elements rather than all of them together, where you get more of a jigsaw kind of pattern. And so that indicated some universality in whatever the formation mechanism was. So just to take a step back, here are some of the images of some of the people involved in this work.
So for these, they have atomic masses with all these isotopes.
Yes.
So they're independent of the model.
That's right. Mm-hmm. So the idea that the two peaks would be produced from neutron captures is basically illustrated here using a typical chart of the nuclei, where you plot atomic number on one axis, Z and N on the other axis. The stable elements are shown with these black dots, forming the valley, so-called valley of beta stability here. And it's proportional to Z with small mass nuclei, but then as you go to heavier nuclei, you get a greater preponderance of neutrons in the nuclei. the rare earth region, lanthanides are in this region here, for example. So if you capture neutrons relatively slowly, where you have years between captures of neutrons, then there's plenty of time for beta decays to keep you very close to stable nuclei. So take a section of this chart and magnify it down here. You keep capturing neutrons onto nuclei, moving up here. And when you get to an unstable one, before you can capture another neutron and progress, you will get a beta decay instead, carry you back to a stable nucleus. And you capture another neutron and beta decay back to a stable nucleus. And as long as there are stable nuclei at larger neutron number, you continue horizontally, but you end up having to work your way up the chart of nuclei sticking to the stable nuclei. Okay, so a lot of these nuclei along this band here are produced by the S process, and the isotopes that are produced only by the S process have an S here. But you can also form some of these isotopes in the so-called rapid capture. So now instead of capturing time scales of order of seconds or months, imagine that the time scales are milliseconds, which is much faster than beta decay time scales. And so now this blue path is pushed way to more neutron-rich conditions, very far away from the valley beta stability. And the neutron capture path then follows something like this. The paths are interrupted by these magic numbers, where you get a weight occurring because those nuclei are particularly stable. So it's difficult to then add another neutron. You rather beta decay to larger proton fraction until you break out again at this point, or this point. And then you capture more neutrons with very few beta decays occurring in between, and you get up to this point. So what happens is that because of the waiting time here, you build up large abundances connected with the magic numbers. And the same thing happens with the S process. So at a magic number, you would, basically the path waits longer here and here, and so you build up large abundances at these magic numbers. But you can see that as these nuclei, as our process ends, these nuclei are radioactive. They beta decay back to normal nuclei, and the beta decay path is a 45-degree line to the northwest. And so you will get a peak then connected with the R process that's located 10 or so units away from the S process peak. Okay, so this nicely explains why there are two different peaks observed and two different distinct processes involved in the production of these heavy elements. We can observe these elements in stars, for example, and this is taken from a paper by Callan, Fieldman, and Trulin from 1991. And the blue jigsaw pattern are the observed abundances of solar system S process elements, and the red curve is the R process abundances. And one can disentangle the two sets of abundances because the S process occurs so regularly that from the abundances of these different isotopes that are S process only, you can infer what the abundances of these intermediate isotopes should be from the S process. But in every case, the total abundance of these elements in nature is greater than what the S process alone would predict. So the difference must be due to the R process. So we can actually determine then the relative contributions of S and R process to these heavy elements. And you could predict the abundances of the S processes, S process for the elements or isotopes that are produced by both processes. And so that's how those two different curves are then can be disentangled in this way. And you see clearly the R process peak to the left of the S process peak. So this leads up to the 1957 paper by Burbridge, Euler, and Howler, famously known as B squared FH. Bada in 1943, 1945 suggested that supernovae of type 1, which are now known to be connected with white dwarf explosions, have a roughly 55 decay exponential half-life in their life curves. And Fowler had observed in nuclear explosions the predominance in the light curve from the emission of gamma rays coming from californium-254. And the half-life of californium-254 is very similar to 55 days. I think it was thought to be at the time 54 days or something. Now I think it's believed to be 60 days. In any case, it was close enough that Hoyle, Burbage, Christie, and Fowler suggested shortly there in 1956 that supernova 1 light curves were actually powered by this extremely gamma ray emission from this and other very heavy elements. And so in the B²FH paper, the first paper that actually categorized different elements by the idea that Coriell had proposed about the RNES process. And so they ended up proposing that supernovae of type 1 make the R process and supernovae of type 2 make iron. So although this paper is very famous, it got the answer wrong for the production of heavy elements. And Cameron in 1959, who's often ignored in these discussions, pushed very strongly for the idea that this idea was wrong and that the R process has to be connected with gravitational collapse supernovae as opposed to lighter progenitor models that make supernovae of type 1, simply because we know that it was believed that they don't collapse to such high densities. So there was this confusion about where the originating site for the R process might be. And Hoyle and Fowler cast a wide net and suggested perhaps maybe supermassive stars, those greater than 10,000 or so solar masses, could have made the R process. And there was so much controversy about the origin site that basically a lot of people changed their focus to just looking at the nuclear properties of the R process itself. And Seeger, Fowler, and Clayton suggested that the R process operates in a gamma N equilibrium, and produced the result that you couldn't make all 3 R process peaks as a consequence in the same event. And Schramm, a little later, solved that conundrum by proposing that instead the R process must occur in an explosive environment where you have expanding material, and therefore you get changing timescales in the expansion, and as a result, you can create all 3 peaks in the same event. So this put us back to square zero as to the connection between the R process and expanding events. I became a graduate student in 1972, and so that's where I got involved. And here again are an interlude with some of the characters here. Willard Fowler was a very famous train enthusiast, and I think he was given this model during a meeting in Wales. So Al Cameron was sort of the competition to Fowler's group. Famously, Chandrasekhar, who was editor of APJ at the time, ruled APJ with a very strong hand, and actually refereed a lot of the papers himself rather than sending them out. And for some reason, had a problem with Al Cameron and his collaborators, and which is why a lot of the early work of Cameron and Truran, for example, appears in the Canadian Journal of Physics rather than an astrophysical journal, because they couldn't get their papers through the referee process. So again, that's not a very good thing. I have written a paper with Hans Bethe, so it was very interesting to see the recent movie in which he is portrayed in there, the Oppenheimer movie. First time I ever saw somebody that I actually knew in a portrayed in a movie. So. Okay, so David Schramm became my thesis advisor. I started life as a graduate student as an experimentalist working on Josephson junctions for millimeter wave observations. I hated it and spent most of the first year of my graduate studies trying to get out of this occupation and convincing Schramm to take me on as a theorist. He didn't want to appear to be stealing students, so it took some time to work this out. But he had a great idea for me. He said he had this sort of intuition that somehow supernovae are not really the source of the R process, that there are problems with supernovae in that, which turns out to be correct. So he was looking around for other possible sites. He was influenced by a paper by the name's escaping me, that appeared in the Vatican Journal of Physics that talked about tidal disruption of stars, one of the earliest discussion of that. And so he thought, well, what happens if neutron stars can be tidally disrupted? And where might neutron stars be tidally disrupted? Well, maybe if they were in binaries with other neutron stars. Well, pulsars had only been detected in 1967. There were no binary neutron stars known, although people were looking for them. And so he proposed this idea to me a few years before the first binary neutron stars were observed. And so that was rather prescient on his part. I actually changed, in order to complete the thesis, I decided I would study in detail the process of tidal disruption in the case that a neutron star merges with a black hole, simply from the point of view that I could then use the black hole as a background, the general relativistic background, and treat the neutron star as a sort of a perturbation on that background. I thought that taking two equal mass objects and studying that in general relativity was beyond my capabilities. So I took the easy way out. And we reasoned that if we found some interesting results from a black hole neutron star merger, we would get even more interesting results if we could do the binary neutron star problem, because of course tidal effects increase as you decrease the mass, as you decrease the mass ratio from a large number to unity. So if it works for black hole neutron stars, it's going to work for binary neutron stars. And we did find that as long as the black hole mass wasn't too large, we could get significant ejection of material. And the nuclear physics of this we also studied, and the dynamical decompression will naturally lead to a kind of an R process. So we submitted our paper to FJ Letters in March of 1974, and it was eventually published in September 74. So the first binary pulsar, B1913 plus 16, was discovered by Hulse and Taylor in July of 1974. But it was only recognized to be a binary in September. And so once they discovered it to be a binary, that's what led to its rapid publication in October of 1974, or submission in 1974, and then finally published in January of 1975. And for context, this was a very interesting time because neutron stars were first discovered in 64, and gamma ray bursts were first detected in 1967, but it was only in 1973 that they became scientifically known because of security reasons. They were discovered by satellites that the US and the Soviet Union had launched to monitor above ground nuclear explosions. And so immediately they were detecting these gamma ray bursts and then telephoning back and forth, what's going on? And they realized they're observing these extraterrestrial, at least atmospheric, if nothing else, events. And so those were scientifically released. Those studies were released finally in 1973, which was just prior to, or at the same time that I began working on this topic. So the reasoning that we took was that you could, although it would seem almost impossible to end up to make a system of two neutron stars. If supernovae in general, massive stars, produce supernovae, you could probably arrange, if supernovae had kick velocities, that in a small fraction of cases, those kick velocities are randomly directed, that they would be directed opposite the direction of orbital motion. And so any mass ejection, which would usually disrupt the binary, could be compensated, and you would end up with a more compact binary with a neutron star. And if the same thing happened after the second supernovae, you would end up forming a pair of neutron stars. We now know that about 1% of supernovae in these cases will not lead to disruption of a system. And so roughly 1/100th% of massive stellar binaries should result eventually in compact objects. Excuse me, binaries. Then gravitational radiation, which was predicted but not observed yet, could be expected to cause orbital decay and an eventual merger. And so 1979, Pulse and Taylor observed the first decay of the orbit from gravitation. Excuse me, now attributed to gravitational radiation. So after millions or billions of years, the components will tidally disrupt and you will get mass ejection as a result, if our ideas were correct. So the decompression leads to a natural R process. The material coming out of the neutron star will have a magic number of around 50, maybe 30 to 60 or something like that, depending on the nuclear mass formula that's used. But a large number of neutrons, and as the material expands, the equilibrium nucleus will become smaller, but the proton fraction won't change because there's not sufficient time for, not sufficient time for beta decays to occur. So you can't change the proton number in the nucleus. And so you come down here, but when you do get closer to the valley beta stability, the relative beta decay timescales and the expansion timescales become more comparable. And so you can then start to beta decay, leading to larger proton numbers. And then instead of shedding neutrons, you begin to recapture them. And you'll run up the path here until you get to nuclei that are simply too large, proton numbers too large, and you'll fission. If this fissioning occurs symmetrically, the fission products will be back down here, and you will then recapture neutrons if there's still neutrons around. And so this makes the classical R process far away from the valley of beta stability, and then these nuclei will then beta decay back to the valley of beta stability eventually. So this seems trivial almost in retrospect to see how this decompression can make an R process. But it was a speculative idea. The favored location for R process has always been supernovae. So the idea didn't really gain much traction. Actually, there were very few citations, maybe 1 or 2 per year for the first 20 years after the publication of this paper, these papers. Because it was such a speculative idea, I got a lot of ribbing from my colleagues about the idea, and I didn't really work much on it following these initial sets of papers. But around the middle to late 1990s, numerical simulations involving general relativity had improved so substantially that people were a little bit bored with just doing supernova calculations, and were looking around for other astrophysical problems to model in general relativity. And so mergers, although there was no substantial reason to believe more that they existed in 1990 than in 1970, became the subject of a lot of intensive theoretical work. And so the citations to these papers started to increase. But the idea that you could use mergers was dissuaded by the fact that you need such a large amount, a hundredth of a solar mass or more per event to explain the observed R process abundances. While in supernova, you would need, 4 orders of magnitude less per event. And secondly, the observations of the oldest, the lowest iron abundant stars, so-called metal poor stars, which are therefore probably among the very oldest stars, all contain R process elements. If they're bright enough to show R process elements, we observe those R process elements in even the most metal deficient stars. So clearly the R process has turned on roughly at the same time in galactic history that iron formation turned on. And since iron formation is connected at least in the very early galaxy with gravitational collapse supernovae, this is a connection then between the R process and supernova. And mergers have a delay time, right, between the supernovae and the actual merger. You need 2 supernovae. And besides that, then you need the gravitational wave decay time, which could be hundreds of millions of years. So that's really why the idea didn't gain traction, because of these major impediments. So the measurements of the R process elements in metal poor stars is rather interesting, because we see the same abundance pattern in basically almost all of these metal poor stars. So this shows 4 different metal poor stars. The underlying curves are the solar system R process, and the symbols, the colored symbols, are the observed abundances of the R process elements that can be seen in those stars. And so you see that they all line up very well. There's not a substantial difference from star to star. So it's a universal process. And these chemical evolution problems basically are summarized here. If you take a model where you get the R process from poor collapse supernova, the simulations predict that the abundance of, say, barium, one of the R process elements, relative to iron, you get a band like this, and the observed abundances in old stars, metal poor stars, falls like this, which is more or less on top of the prediction. But if you have neutron star mergers, those mergers don't turn on until the iron abundance is already built up substantially, and so you can't explain these optics. One advantage of the merger scenario, though, has always been that there is a large scatter in our process abundances, especially as you go to more and more metal deficient stars and probably older stars. And so this wider scatter indicates that the event that's producing the R process is rare, or implies that the R process is rare rather than common, as so you can't get it from a typical supernova. It has to be possibly a rare type of supernova, as opposed to every supernova, if it's a supernova origin. But mergers are obviously rare, so they satisfy this constraint. But as the years accumulated and models of supernovae became more and more developed, it became quite apparent it's almost impossible to make our process in supernova ejected. The material is not neutron rich enough. And furthermore, the neutrinos emerging from the protoneutron star tend to protonize the matter rather than neutronize it. So even if you began with a rather nice neutron excess, you would quickly lose that advantage as the neutrinos interact with that material during the expansion. And then, as I said, the merger simulations became much more possible, and therefore, if it's possible, it gets done. And by the year 2000, there were many, many groups pursuing mergers, and they began to show that in addition to tidal ejection, which we had discussed, there were also other possible mechanisms: shock heating, the neutrino winds that could drive material from the rapidly rotating protoneutron star, or rapidly rotating remnant before black hole collapse. and so on. So that there are many other ways mass can be ejected in these events, not just tidal disruption. And there also became predictions then for what this material might look like optically after it was ejected, when it was realized that yes, these gamma rays could produce an afterglow. During the 2000s, a paradigm shift occurred in how we believe our galaxy has formed. Instead of forming as a integral massive object beginning, it's now believed to have been built up from the mergers of small pieces. And so this presents an interesting possibility that nucleosynthesis history in each of these small pieces is rather different. And you could possibly then, in a model, in modeling the nucleosynthesis, break this connection between the iron abundance and time. So it's no longer obvious then that low metal abundance is connected with being old. So that gave some new galactic chemical evolution models were produced that basically established that maybe the merger scenario, even with a substantial delay time in the merger, could be produced. We've also realized, however, that the original stars had low metallicities and therefore were probably more massive than stars today. And the neutron star binaries that would be produced would have different characteristics such that they probably merged with a shorter delay time than would be the case today. So all of these things began to become more favorable toward the idea of having mergers be involved. So Lee and Paczynski were the first ones to really emphasize that the gamma ray burst afterglows that were observed could be produced from heated R process ejected by the beta decays that occur. And these gamma rays would downscatter that appear as optical emission after the event. And there were a few cases where, well, this is a famous one where there was one point that was too high, and so this was thought to be then a detection of a kilonova, which is a pretty weak evidence, but it was one of the first ideas. And so here you see a little glow here that pretty much appears that just a month later, so that there are evidence began to build up that kilonova-like events are connected with some short gamma ray bursts. There was also interesting development in the 2010s in terms of chemistry. Wallner et al. Were the first to detect plutonium-244 in ocean sediments, and the detections prior to that were upper limits, and so they were the first work to actually establish an abundance with error bars. And but interestingly, they showed abundances that were rather small compared to what the abundances should be if the R process is connected with basically virtually every supernova. Here's a blackboard figure by V. Perron that kind of shows it. If you have frequent events, if every supernova produces some plutonium-244 in small amounts, then you produce it, it starts to decay. Before it decays too much, there's another production event, and so on, so that the typical abundances that you would observe would be relatively large at any given time. But if the events are rare, then the typical abundances you should observe at any time, well, of course, if you're near an event, you would observe a high abundance, but on average, you should observe a low abundance. So these observations are then characteristic of something that's very rare as compared to a typical supernova. So this is evidence then that could be used to justify the merger scenario. Another example came from looking at ultra-faint dwarf galaxies. So you have galaxies, you have dwarf galaxies, and then you've got ultra-faint dwarf galaxies. Ultra-faint dwarf galaxies have masses of only a few thousands of the solar mass. And interestingly, there was a study of 10 ultra-faint dwarf galaxies that were close enough and had stars in them bright enough to show our process elements. But a detailed study of stars in those 10 ultra-faint dwarf galaxies showed that only one of them had detectable R process elements, and the other 9 did not. So this was further indication that it must be a rare event, because 9 of these galaxies have existed without a single merger event, and 1 of the 10 actually had 1 or more merger events. And in fact, from the detected abundances, you could figure out that the total amount of R process elements in this one ultra-faint dwarf galaxy that had R process elements discovered, reticulum-2, was in fact consistent with 1 merger event having been occurring. In comparison, thousands of supernovae have occurred in these galaxies up to this point. So again, that ratio is also interesting. It's about what we would expect. So this is somewhat controversial now. There are other ideas that have been proposed to explain this behavior, but at the time it was considered to be rather interesting evidence that mergers might be, or at least a very rare supernova might be the production source. So let me skip the rest of that. So Zvi Perron produced this another nice figure. From the total abundances of R process elements in a galaxy, you can make a band, considering uncertainties in those abundances, and plot it as a function of rate and the amount of mass ejected per event. So the product of these two quantities has to be the same as the R process abundance. So you get this band. And if you then look at the available pieces of evidence, plutonium-244, for example, is gives you this blue region. Soft, the abundances of soft gamma ray bursts, short gamma ray bursts, gives you this kind of band here. The number of compact binary systems in the galaxy, predicted bands for the rate. In this way, the observation of kilonova from short gamma ray bursts gave predictions for the amount of mass ejected from the brightness of those kilonova in this range. UW170817 gave an estimate for both the rate of merger and the amount of mass ejected per merger. So the box here. And so everything seems to be lining up in an interesting area. So there are many different pieces of evidence that we're now suggesting that mergers could in fact explain most of the R process elements. So the question arises now, what if GW170817 has produced the necessary evidence to say that the problem is solved? And unfortunately, we are going to need more confirmation of this. The detailed evidence from GW170817, the kilonova that was observed, there's no substantial evidence that anything heavier than the first R process peak, that any elements heavier than the first R process peak were produced. We don't have enough knowledge of lines from the heavier R process elements, and the observations were, even as close as this event was, weren't good enough to see a lot of those lines. So we really have no direct evidence that anything really heavy was produced in that event, other than at least something connected with the first R process peak. So we still need more evidence to claim that this is the actual idea. Meanwhile, there are other suggestions going on connected with both rare supernovae and with an interesting new idea that is connected with magnetars. So what's a magnetar? A magnetar is an extremely magnetic neutron star. They tend to be very slowly rotating because the magnetic fields have basically caused the rotation rates to decrease substantially. We don't know how many neutron stars are born with these intense magnetic fields. So magnetars have magnetic fields on the order of 10 to the 15th Gauss. Normal, young neutron stars like the Crab Nebula, 1,000 years old, Crab supernova, have magnetic fields about 10 to the 12th Gauss. And there's no way that the Crab Nebula could have been born with such an intense field. So we know that some neutron stars are produced with these high fields. We also know that the fields will rapidly decay. They get pushed out of the star. It's an unequal, it's not a long-term stable situation to have such an intense field inside of a neutron star. There are tremendous forces trying to eject the magnetic field. So it's believed that the magnetic field is pushed out from the interiors of these stars, and you have field reconnection near the surface, and this creates huge flares and magnetic storms. And they're observed as gamma ray flares. So we have seen 3 very large gamma ray flares. We know of about 29 magnetars. These flares are not very common, but they are believed to be connected with magnetic field recombination or reconnection on the surfaces of these stars. And as a result, magnetars have a very short lifetime. So in fact, there might be as many magnetars born as normal neutron stars, even though we only know of about 30 magnetars, and we know of over 3,000 neutron stars. The difference in times when a neutron star can be a pulsar and when a neutron star can be a magnetar, could balance it so that the populations of the two objects might be initially quite, or the production rate might be quite similar. So here's an idea that appeared in a recent paper by Patel et al., built on prior work. But the idea is that you have a magnetar in which the magnetic fields are recombining as they're ejected near the surface. It shocks the surface of the crust and ejects material. And the material eventually escapes, and it's possible to then make our process out of this ejected neutron star material. So here's the light curve for one of these events, the soft gamma ray repeater 1806-20, which was observed in December of 2004, one of the 3 known giant flares that have been observed. So it has a total luminosity, gamma rays plus X-rays, that appears to look something like this. This time scale is logarithmic. So it's believed that this pattern here, where you get increasing frequency in the oscillations, you're actually not increasing the frequency. The frequency is constant because it's on a logarithmic scale. But this is rotational modulation of the X-rays being emitted here, connected with the spin period. And so the idea is that you get shock heating of the neutron star crust by the energy released in this magnetic reconnection. The total energy released is around 10 to the 45. But I'm sorry, that the luminosity is around 10 to the 45 Earths per second. Total energy release is around 10 to the 45 Earths because the time scale here is in 1 second. And so this ejected material, you have modulation by the spin of the star as it goes in and out of view. Because this flare occurs only on a localized region of the star. So you get the spin modulation as a result. And then at late times, you get theoretically, you would expect an increase in luminosity coming from the nuclear gamma rays produced in the subsequent R process that's occurring. And what hadn't been realized was that when you look back on gamma ray observations of this source, then in fact there were 3 different gamma ray satellites that were observing the source after the flare, and they in fact saw this increase in gamma ray luminosity. And this connection really hasn't been put together until now, that perhaps this excess gamma ray emission that occurs at these late times, thousands of seconds after the event, involving a total peak luminosity of around 10 to the 39 joules per second, could be connected with the radioactivity from the R process. So estimates that fit the fluence and light curve of this particular event suggest that a total ejection of about 10 to the -6 solar masses of R process material was neutron star material that became the R process was produced. And the galactic event of these magnetar flares is estimated to be about 1 for every 100 years. And if you take this amount of ejection and multiply by the galactic rate, you would suggests that 1 to 10% of the observed R process abundances could be due to these magnetar flares. So this doesn't suggest that magnetar flares are responsible for all R process, but could be important contributors. And where these contributions might be most important would be at early times in the history of the galaxy, where you still would have a problem of the delay time of mergers and the fact that the R process and iron both turn on in abundances at about, very early. So it's still a thorny issue, but this alternative source connected with these flares on magnetars might be able to fill the gap in at early time. So maybe the combination of merger events plus magnetar events could mean that we could put the idea of supernova contributions to the R process to rest. So I don't know what the final story will be, but so it's an ongoing situation. We need more gravitational wave events to pin down the merger rates. We need more kilonova observations to pin down the total amount of mass ejection and to get definitive line information that proves that the heaviest elements are formed in this way, and so on. So anyway, thank you for your attention.